At low air speeds, and therefore low dynamic pressures, the effectiveness of all flying controls for a given displacement is reduced. This effect on the rudder has already been mentioned, but the ailerons are similarly affected, of course. To obtain the required response, greater deflection must be used at low speed. The downgoing aileron will add to the yawing moment from increased induced drag, and may even stall the outer section of the wing at low IASs. Adequate aileron effectiveness is clearly very important, since VMCL requirements include rolling and not just directional control. JAA's document CS 25.149 sets out the criteria for establishing the various minimum control speeds for the certification of a new aircraft type. Once established, the speeds will be included in the aircraft's flight manual. From the extracts that have been detailed in this lesson, we can summarize several significant points. First, regarding VMCG, nose wheel steering may not be used when establishing the speed, since its use would artificially reduce VMCG, and on a slippery runway, nose wheel steering is likely to be ineffective at speeds well above taxiing speed, so would not be able to control the aircraft directionally at or above the stated VMCG. For VMCL, the criteria include a roll requirement, and not just one for directional control, as with the other VMC categories. As a general point, the thrust developed by an engine depends on air density, so thrust will decrease with increasing altitude and temperature. The yawing moment due to asymmetric thrust will thus reduce with altitude and temperature, enabling control to be maintained at a lower IAS. VMC therefore decreases with higher density altitude. You learned in the earlier flight mechanics lesson on climbing that an aircraft's ability to climb depends on the excess thrust available after aerodynamic drag is balanced. If a twin-engine aircraft loses an engine, thrust is reduced by 50%. But excess thrust, that is, thrust minus aerodynamic drag, is reduced by more than 50%, as shown in the graph on the screen. The ability to climb may be reduced by as much as 80%. The angle of climb is determined by the excess thrust available, and will be a maximum when the aircraft is flown at the speed where excess thrust is at a maximum. In other words, at a maximum thrust-drag ratio. Since thrust decreases with forward speed, and total drag increases above and below the minimum drag speed, VIMD, the best angle of climb is achieved at a speed below VIMD, but at a safe margin above the stall speed. The IAS for best angle of climb is Vx for all engines operating, and on twin-engine aircraft, VXSE is best for single-engine climb angle. Rate of climb is determined by the excess power available. Power is the rate of doing work, that is, thrust or drag times true airspeed, thrust and drag being forces, and TAS being the only real speed. Although thrust reduces with speed, total power available increases to a point because of the speed factor. Similarly, power required is a measure of drag times TAS, so excess power available determines the available rate of climb. The airspeed for best rate of climb is Vy for all engines operating, and Vyse for best single-engine rate of climb. Vy and Vyse are higher than Vx and Vxse, and provide a safer margin above both stall and VMCA. Under most circumstances, Vy and Vyse are the best speeds to use. On small twin-engine aircraft, Vyse is marked on the airspeed indicator by a blue radial line, and is referred to as blue line speed. Considering all the foregoing factors, we can conclude that at a given altitude, airspeed and power setting, excess thrust depends on the amount of drag being generated, and this in turn will depend on configuration, weight, and whether turns are required. The control surface deflections required to balance asymmetric thrust will also cause drag. It is essential, therefore, that after an engine failure, particularly during takeoff or go-around, drag is reduced and no turns are made until safely clear of the ground. Drag can be reduced by feathering the propeller of the failed engine, raising the landing gear, raising the flaps at a safe height and speed, closing the cowl flaps on the dead engine if fitted, and applying 5 degrees of bank towards the live engine. Flying at blue line speed, Vyse, with maximum permissible thrust on the live engine, will provide maximum performance and optimum control of the aeroplane.